Hi, my name is Jesse. So I'm presenting our work, ReWiND Language Guided Rewards, Teach Robot Policies Without New Demonstrations. So to get an intuition of our approach, let's start with an example. Imagine you wanted to play basketball, right? Right now you're in LA, you would go maybe look at the Lakers for inspiration. You'd see greats, Bryant, LeBron James, right? After seeing this, you might ask, how does one get to being this good at basketball? I would argue that it starts with having a great coach. Many great coaches share three core traits. First, they provide detailed feedback even when you make mistakes. Second, they generalize their guidance to various basketball skills needed to play at different skill levels, whether it's at college, on the street, or all the way to the NBA. Finally, they adapt their teaching style as your play style evolves. Skilled coaches are necessary for basketball players to master every skill needed in basketball. Now, what would a skilled coach look like for robots, right? In robotics, a coach, or maybe more generally a teacher, is like a reward model. Just like a great coach, a reward model should be able to enable our robots to learn new tasks by one, providing detailed feedback even when the policy is failing. Two, generalizing the unseen tasks the policy and or the reward model has never seen. And of course, three, being robust to different ways the task is specified or different ways the policy is attempting to perform the task. The challenge here is, how can we train such reward models scalably so that they don't need a lot of demos for every new robot setup or collecting a bunch of failed demonstrations to really train this reward? We address these challenges with ReWiND, rewards without new demos. The goal here is to pre-train a reward model that allows a robot policy to learn unseen tasks that neither the reward model or the policy has seen before. To do so, the reward model requires just 5 demos per training task. After a human collects the data, we then train a reward function and offline RL policy, and then deploy the policy with online reinforcement learning, where the rewards are coming from the densely labeled, dense rewards are coming from this language conditioned reward model. This results in real world learning of unseen tasks in just 1 hour. So given only successful demonstrations without any prior reward labels, we use a very simple and stable progress prediction objective to train the reward model. For example, in this demo of a robot picking up a cup, progress is defined simply as the current frame divided by the number of total frames. This objective directly translates into a 0 to 1 normalized dense reward that we can use for training an RL policy. But if you look at this, only training on successful demos is not going to give you a good reward function that actually rewards properly for when the policy is failing. But that's really important when you're learning a new task because you won't be successful from the start. Therefore, we introduce a video rewinding objective that generates failed trajectory examples from the successful demonstrations to train the reward model with. So let's say we take the same trajectory and rewind at the fourth frame. The robot's about to pick up the cup, right? Until the 4th frame, the progress target increases just like normal. We split at the 4th frame and we rewind 2 steps, randomly sampled. And we have a decreasing progress target that now looks like the robot is actually dropping the cup. And the rewards for training the reward model appropriately scale with this decreasing objective. So now we have a demo that looks like robot drops the cup and the reward is going down and the reward model is able to be properly trained to reward this type of behavior at a lower reward than if it was successful. Here we still again have dense reward labeling for each frame. Finally, to encourage generalization to unseen tasks, we additionally train this reward model with a subset of the OXC dataset so that it can better generalize and is more robust to how the policies actually solves the task. Okay, so are these things actually enough to train a good reward model that's very data efficient and can allow you to learn new tasks? The answer is actually no. We had to design the architecture very specifically to bias it towards generalization to out of distribution instructions and video sequences for different tasks. What we do here is we feed the language and video inputs to a pre-trained mini LM and dyno embedding. We then project these to a shared embedding space for we call it a cross-modal. So sequential aggregator. It's really just a very straightforward transformer network that's causally masked, which predicts an embedding for each input image frame. These embeddings are then converted into the predicted reward objective. We, of course, need to give the model positional embeddings, right? It's a transformer, so that it can distinguish reversible tasks like pulling versus pushing, opening versus closing. But if we give it positional information here for every single frame, it can actually just cheat and overfit and directly use that positional information to predict the reward. Therefore, inspired by Jason Ma's prior work on generative value learning, we actually only give positional embeddings to the very first frame, which allows it to not overfit to just using positional embeddings to predict the rewards, yet distinguish between different types of tasks more effectively. We start our analysis and simulation in MetaWorld by analyzing reward function performance on unseen tasks. Here we plot confusion matrices that plot the reward videos and language instructions of unseen tasks against a bunch of baselines. The goal is to have a really solid diagonal because that is where the aligned task should have the highest reward. There's all the baselines. They kind of suck. Here's ReWiND. ReWiND, even without OXE data, is able to get a much better confusion matrix. This also applies to the real world, where again, ReWiND gets the best confusion matrix by far. Then we evaluate policy learning with ReWiND on new tasks in MetaWorld. So compared to baselines, ReWiND in red outperforms on 8 unseen tasks with image-based offline to online RL. We also perform real-world RL on a low-cost 30 Hz by manual manipulation setup, where ReWiND enables real-world learning of unseen tasks in just 1 hour of total experiment time. We compare against VLC, which is one of the best performing reward baselines on our offline metrics in the paper. Here's the pre-trained performance. It's not very good, but these are a lot really hard tasks that have been seen. VLC after online RL for an hour doesn't really improve. ReWiND, on the other hand, has similar pre-trained performance, not very good, but improves much, much better after 1 hour of online RL. Here's an example video where I can talk about what is actually learning. So after about 20 minutes, this is an example of opening this red trash bin. We kind of see like an aha moment, to borrow DeepSeek's terminology, where the reward model eventually overpowers the original pre-trained policy, where the policy kind of learns to slow down and really firmly put its gripper underneath that red trash bin to open it. The pre-trained policy was much faster because that is how the demos were collected. So to wrap up, I'm just going to play this video of real-world training over an hour, sped up by like 20x, to show how it's learning this towel folding task. Number of cumulative successes are increasing over time, and I will happily take questions. Thank you.
So the reward model takes the action, the language instruction, and the history of observation as an input. It doesn't take the action as an input.
It does not, and that's because we want it to be cross embodiment. So we were able to train it on OXE dataset. Theory, you could train it on human data, but it is action agnostic.
How does it affect your online learning learning algorithm if you don't have the action in your report?
Right. So that it's basically just based on progress towards the goal, essentially, right? Like finishing the task. The action is implicitly encoded through whatever next observation you see. I think if we were able to solve the cross embodiment problem and include actions, it would be a better reward model. But we aren't able to test that. Thank you for the question.
I think it's a very interesting work. So when you construct your model, specifically when you construct your negative science, it looks like you are recombining frames from the successful demos.
Yes.
So does that mean like the negative demos only say the states that the successful demos visit? So for example, you will never be able to say collisions some other nuanced failures. And does that also mean your recording will actually capture this perspective beyond?
Yeah, that's a great question. It partially can, but mainly because we are training on OXE data also, which is quite noisy. But essentially, we can't generate new states without some kind of image generation thing or simulation or stuff, which is a lot less scalable. So our focus here was just getting a good reward model with the limited amount of real world data that we have.